Good evening, everyone. I am back with my webinar series. This is going to be our 36th number webinar, supported by EEC and IEAM on a very crucial and important topic of transformer explosion and fire protection systems using FDS, Fast Depressurization System. First of all, it is mandated to understand what causes a transformer to catch fire. A transformer can catch fire as a result of electrical and mechanical failure. When I say mechanical failure, that may be the damage to components of transformer because of extreme weather conditions, some seismic activity, physical handling during shipping and installation, last but not the least, the transportation damages. When I say the electrical damages, it includes insulation failures, problem in the core, voltage surges, partial discharge, loose contact, ED currents, OLTC failure, thermal overloadings. And during faults, what happens? An excessive amount of energy flows in the transformer, leading to fire and explosions. There mineral oil, usually mineral oil is there for the insulation and cooling purpose in the transformer, having some flash point of 140 degrees Celsius and fire point of around 170 degree. As a result of the high temperature because of some mechanical electrical faults, the decompositions of mineral oil starts. There is a generation of different gases, and because of generation of gases, the pressure inside the transformers increases, and in that case, there may be rupture of the tank, and because of that, there is a release of energy, strong thermal radiation that includes flaming oil, solid insulation, molten conductor. Mineral oil fires separate to surrounding equipment and buildings that need install some physical separations and firewalls. Now, I would like to give some data available on the public domain. In the last 4 years, 29 to 21, as per the data available on the site of CA, there were 33 major transformer reactor failure. 220 kV failure were 10, and 400 kV 19, and 765 reactor and transformer included 4. If we talk about the reasons of all these failure, I have mentioned tap changer, bushing, core, winding, cooling system, tank failure, and contribution of each factor 50% as per the report is because of the winding insulation, 9% because of the aging, 8% because of winding, and for reactor 22 attributed to bushing failure. It is worth to mention here that with a significant number of transformer and reactor failing, and the failure sometimes leading to the extreme consequences of fire and explosion, they need to have some fast technology to prevent this fire and explosions. Having understood the need of latest technology and the discussion required, I have arranged this special webinar to understand new FDS technology, fast depressurization systems, which is also advocated by and recommended by NFPA 850, which subject matter expert, respected Rahul Sood ji. Before I give introduction of Rahul Sood ji, I would like to thank Almighty and my family, that my parents, my wife, my son, my mentors include respected PP Bhai Saab, Anju Chandra ma'am, Dr. Kamal Bansal sir, Murthy Saab, NK Mittal Saab, respected P. Ramachandran sir, S. Abhav sir, Hitesh Chauhan ji, Arvind Tukral ji, Sanjay Agarwal ji. My friends and my well-wishers include Saket Gupta ji, Umesh Gupta ji, Amandeep ji, S.K. Batra ji, Dr. Vikas, Pradeep Garg ji, and last but not the least, my team working day and night to making this webinar to happen includes Gulab Ram Dhani. Now, time to give a brief introduction about today's presenter, Rahul Sood ji. He's a basically mechanical engineer. He's basically mechanical engineer with professional degree in MBA from Indian Institute of Planning and Management. He's a dedicated and dynamic professional who has consistently delivered outstanding results through strategic planning, market analysis, and effective team management. He has been working with Sergey for Sergey transformer protection since 2009. He's a business development manager for Southeast Asia and India. He is known for providing solutions for complex issues, and he's providing technical and sales training to channel partners and the sales teams. And he has revived business in Indonesia, Vietnam. He has introduced agri-technology in various renowned utility in South Asia, and he also achieved a significant milestone by securing a landmark order valued 1 Indian rupees in railway sector. In short, he is a result-driven business manager providing solution with respect to fire in the transformer, helping utility to understand new technology, FDS, fast depressurization systems. Let's hand over this stage to Rahul Sood to set this stage on fire with the knowledge he has. Welcome, sir. Welcome to Igniting Power Engineers.
Thank you, Dr. Rajesh Arora ji. I welcome all the respected intellectual officials from the power industry, all the members out here who have taken out the time to be a part of this webinar. I am extremely thankful to Dr. Rajesh Arora ji for organizing this event, and the job Igniting Power Engineers as a platform is doing. It's really appreciating. And I have gone through the few webinars which have been conducted before, and I see the interest of the people. I've been member of this, the group which has been created, and I'm being a part of this group. Not been a long time, but I have seen the queries being posted. I've seen the interest of the officials, and of course, most importantly, uh, to come up with a topic wherein people want advice, which makes this platform a really great one. And I'm really proud to be a part of this group, wherein sometimes somewhere one or the other query which I normally have related to transformers or others in the power sector, I get it directly or indirectly, because we have several officials here who normally discuss, the issues we have been facing in, daily managing power sector in daily life. So, which is really interesting and adds to my knowledge when I normally get in discussion with the people or the utilities in India or outside India. So, a big salute to Igniting Power Engineers. As Dr. Rajesh Arora ji said, yes, I have been associated with Sergey for last, almost 15 years now. I'm taking care of India and Southeast Asia, and it's a really good platform for us to actually, present fast depressurization technology, which is used to prevent explosion and fire on the transformers. Right. Talking a bit about Indian market, yes, Indian market is very, I would say, interesting market. Highly technical officials are being part of it, which make it more interesting. Not only to discuss about technology, but to learn a lot of stuff. Comparing with other countries, India is having almost, we have 29 states wherein we have individual utilities, which is almost like 29 countries around Southeast Asia, so which is not small. So it's a pleasure to be here. Without taking much time, I would like to start my presentation with due permission from Dr. Rajesh Arora ji.
Please go ahead, sir.
Great. I'll share my screen, and I would appreciate to have your comments whether you are able to see my screen or not, so that it would be easier for me to uh, so are you able to see my screen?
Yes, yes, it is visible. Go ahead, sir.
Okay.
Make it full screen.
Yeah.
Okay, it's okay. Perfect.
Okay, great. I hope my screen is visible to everyone.
Yes, yes, everyone.
So again, here we'll be talking about Sergey Transformer Protector. Sergey is actually a French company, and we have been into this business since 1954. This company was actually started by EDF, which is the national utility of France. With the current management taking over in 1980s, by that time, few technologies were developed, which was Sergey 1000, 2000, 3000, which was mainly on the extinguishing side, extinguishing fire on the transformers. But with a rigorous research program, which started way back in 1995, and we were able to develop a technology, fast depressurization systems, in 2000. And since then, we have been manufacturing and promoting this technology and doing regular developments on the same with respect to the feedback or the advices or the suggestion we receive from the intellectuals from this particular industry. Going further, Transformer Protector is a fast depressurization system in compliance with the recommendation from NFPA 850 of year 2010, 15, 2020. And it gives a complete protection to the transformer. We protect main tank, OLTC, oil cable boxes, and bushing turrets. As I said, this technology has been recommended by NFPA, which says fast depressurization technologies have been recognized, and recommendation for the use of these technologies are now included. And then they explain what they exactly mean by fast depressurization systems, a passive mechanical system designed to depressurize the transformer a few milliseconds after the occurrence of an electrical fault. So the keywords out here are passive and mechanical system, which can actually depressurize the tank within few milliseconds. Well, this is course of my presentation, but we would be considering the time we would be focusing mainly on the principle and of course the life tests which have been performed and other aspects, including the configuration and why the existing protections are not efficient to prevent explosion on the transformers. Well, I start with this slide which talks about, as we all know, that power transformers are very dangerous. The reason being large quantity of oil is in contact with high voltage elements, and as such, there is no standard international security norms for the transformers. Now, this picture which you see on my screen, it's actually a CCTV footage of one of the hydropower plant, which Itaipu hydropower plant, which used to be one of the biggest hydropower plant. Now, unfortunately, one of the transformers out there exploded, which was a result of a short circuit inside the transformer, generation of explosive gases, which deforming the cover of a transformer, looking for oxygen, and taking over the complete corridor. Just for information, the whole power plant was out of service for 4 months, and this section was out of service for 13 months. And unfortunately, 2 people got badly burned. Now, here to show why this slide is there in my presentation is just to give you an idea, and I'm sure people are very well aware that how devastating an explosion can be. And despite having the standard protections which are available in the substation or the protection with which transformer actually comes in, still there are cases, or I would say many cases worldwide, wherein the transformer is exploding and getting on fire. Now, we all know if there'll be a transformer explosion, there'll be huge fire, human life risk, plant outage, environmental pollution, and of course, company reputation, and not to be missed, financial losses. Few cases, again, just to highlight the point that these transformer explosions are not something new, and it is there and still having all the protection in place, which is a standard one. The transformer explodes. Case of Krumel nuclear power plant, and there are many others. Picture of a transformer which exploded. Blinod coal power plant, then picture of the transformer which exploded. Now, going further, we have conventional ways to fix this, which comes under corrective means and preventive means. And we have bifurcated as it's shown in the presentation in front of you. So corrective means we talk about firewalls and fire extinguishing systems, which covers water-based system, high velocity water spray system, emulsifiers, any extinguishing system. So corrective means are mainly to limit the propagation of the fire. So important to note here is that firewalls and fire extinguishing systems are there to limit the propagation. They are not actually working to prevent explosion on the transformers, right? So these technologies as there, let's say in case there is a fire or explosion on a transformer, this will ensure that the fire do not spread from one transformer to another and it is extinguished. But they are not working to ensure that there is no explosion or fire. So we have again few cases, it's bit old cases, but just for your reference, wherein these few cases wherein even though fire extinguishing systems were there, but still fire propagated from one transformer to another, which is a case in US, and few cases again in US, Ineos Venice plant. So now here the point is that if we are working on to prevent explosion on the transformers to avoid fire, we will at a large extent will be able to solve the purpose of wherein we call, say, limit the propagation of the fire. Now, coming on the preventive means, every circuit, every substation has circuit breakers. Every transformer comes with buckle relay. Not every, when sudden pressure relay is something which is an optional. Gas monitoring is an optional. It depends on end user whether they want to go for it or not. PRV, last but not the least, but PRV is something which comes with every transformer and it is a mandatory. But despite the fact transformers do have PRV, which are mainly to prevent explosion, but the cases which are there, which I've shown you quickly in my previous slides, they were having all these preventive means, but still the transformer exploded. So herein, to give you an overview of last 10 slides, which we said that despite having the mandatory protections on the transformers, despite having the corrective means, we still facing the cases of transformer explosion and fire on the transformers. So looking at this, there is a technology we worked on, technology we developed, technology we researched, and we call it a transformer protector. Depending on arc location and transformer size, the TP is activated within 0.5 to 20 milliseconds by the first dynamic pressure peak of the shock wave, avoiding transformer explosion before static pressure increases. So now here the figures which you see on your screen, 0.5 to 20 millisecond, is something which is not random. It is a result of several live tests which we have conducted in the lab owned by EDF and CIPL in year 2003, 2002, 2004, 2022. So we have done series of live tests wherein arc is actually created with the help of electrodes inside the transformer to see with TP adapted on it to see how fast TP activates with different rating of a transformer and different sizing of the transformers to see the maximum possible time a TP takes to actually depressurize the tank or TP takes to get activated and depressurize the tank. So we found as a result of these tests that TP always activate within 0.5 to 20 milliseconds depending on the size of the transformer and the application. Now, as Mr. Dr. Rajesh Arora perfectly mentioned, why do transformer explode? So I won't be putting much time here. It's just very quickly, we have an insulation rupture. There are impurities which result in the generation of an arc. The gases from this arc goes to the oil. The density difference result in the formation of gases, forming a bubble around the arc. Now, the density difference between gases inside the bubble and the oil outside results in the formation of dynamic pressure peak, which propagates inside the transformer at the speed of 1200 meters per second. And when these waves get converted into static, which is very uniform, results in an explosion of a transformer. So what we do with this sequence of transformer getting exploded, we break this sequence. With the first dynamic pressure peak shockwave inside the transformer, our system gets activated and we depressurize the tank to ensure that there is no explosion on the tank. Let's see how. Now, this slide in front of you, it's a pictorial representation of our system. Herein, we are only showing the protection for the main tank, right? Because the principle remains same when we talk about OLTC and the protection levels on the transformers. So herein we have, we call this particular component as vertical depressurization set. It has a rupture disc inside. This rupture disc is actually stainless steel, to be precise, 360L with grooves. Now this rupture disc is calibrated based on your transformer, and that is placed in a sequence inside this decompression chamber. We call it as vertical one. Now this decompression chamber could be on the sidewall of a transformer or it could be 45-degree. That purely depends what your transformer is and how your transformer is designed and how your substation layout is. Our aim remains to be compact and efficient as much as possible. Now here we are showcasing vertical depressurization set. Here we have, the OGST tank, oil gas separation tank. Now this tank, we have different configuration for the same. It could be mounted on the wall as it is there in front of you. It could be a part of a conservator tank, which is only feasible during the manufacturing of a transformer. So we request transformer manufacturers to extend this conservator tank, give a partition, and the following part serve as a OGST tank, and we call it as slice OGST. It could be elevated above the conservator tank. So we have different configuration. Here in coming back to this picture, this is called wall mounted OGST, oil gas separation tank. And here we have a cabinet which has nitrogen cylinder inside, and this is a pipe connecting, nitrogen cylinder to the transformer tank. So let's see what happens. Before that, I would like to tell you that size of this depressurization set differs for different rating of transformers. Normally, TP has sizes ranging from 6 inches to 12 inches, and after that, we multiply the set. Now, normally, just for your information, like for 100 MVA, we have a DS which is 10 inches. Then when we go, 8 inches, then when we go up the rating, the size increases, right? Depending on, very common thinking that the oil content is more, then of course, to ensure the fast depressurization and enough depressurization, we have some sizing calculation which we have researched, and we follow the same. So it ranges from 6 to 12, and after that we multiply the DS on the transformer. So let's see how it works. There is an arc inside the transformer. There are, as I said, bubble of gases. The density difference between oil gases inside and the oil outside, dynamic pressure peak will propagate. And when it strike our system, the rupture disk burst because of actual pressure rise, and the oil moves to a separate tank. Now, once the oil has moved to the separate tank, the oil flows back because of gravity and stabilize its position because of the equilibrium. So on all three sides, it would be same level of oil. So once the tank is depressurized, the nitrogen is injected from nitrogen cylinder to ensure what all explosive gases are there are, neutralized and kicked off from the transformer to the atmosphere outside. So very simple process. I'll play it again. You have an arc, bubble of gases develops. The density difference results in the formation of dynamic pressure peak. It strikes the wall of our system, the rupture disk of our system. The rupture disk bursts because of actual pressure rise. Oil moves up to the separate tank, depressurizing the tank. The oil flows back. It remains in a closed circuit. The tank is depressurized. Now the nitrogen is injected so as to ensure that what all explosive gases are inside, it is neutralized and it is taken out from the transformer to the atmosphere, so that when somebody open the cover of a transformer to see the transformer from inside, there won't be any bazooka impact. So the system works in two modes: preventive mode, wherein we are not dependent on any signals to activate our system. It's completely mechanical. There is a rupture disk which burst. It's a result of a mechanical burst. And then we have nitrogen injection getting injected, which is of course based on the signals from the rupture disk and one of the electrical protection. So the important part is prevention, which should happen within milliseconds. And there is a reason for it, because within milliseconds, we have enormous amount of gases, being produced as a result of a short circuit inside the transformer. If we are not taking care during those milliseconds, there is a high probability of getting transformer exploded. During the course of my presentation, I'll show you one of the videos wherein we have actually taken, through high speed cameras, how arc converts into a plasma within I would say, milliseconds. So until this point, are there any queries, or I would move to the next part wherein I would be showing you the videos of our live test, videos of our, the test we recorded during the movement of arc, and why PRV is not efficient, and some of our configurations along with the design and the credentials. So this is the basic principle. So any queries until this point, I would be pleased to answer here
We
itself.
will take question at the end of the session.
Okay, perfect. Perfect, Rajeshji. So let me move further. Okay, so herein we have, this is a quite interesting video, and in fact, it's actually a live test which was done way back in 2004. And you will see here how TP is installed with the transformer, and how it activates when the arc was fed with the help of electrodes during the test. So let me play this video. So herein you can see that our system is adapted on the side wall of the transformer, and it has a glass plate. It has put with an intention to see how oil, the tank get depressurized and the oil moves out of the transformer, and the arc is fed from the completely opposite side with the help of electrodes. So that the dynamic wave actually has to cover the maximum distance to reach our system. Sorry. So let's see what happens. I'll play it again, explaining the same. So the DS is here. The arc is fed with the help of electrodes through the completely opposite side, and the dynamic wave propagate from here to activate our system. So this test is actually one of the live tests, and after that, we before that actually we did one in-house test, because when we were getting ready for these live tests, there was not even a single software which could actually cover the parameters of a transformer explosion. So before taking the system to the lab, we worked on a simulation, and we wanted to test that simulation, so that because these tests are quite expensive, so we should have some results in our hand, and on our research, so that based on that we can take our system to the lab. So this is one of the in-house tests which was conducted. So let me play it for you. So here you can see it's a small reservoir, right? And the aim was to check our system, how fast the system acts. So an arc was generated here in a small reservoir to see how the system gets activated and how fast it depressurizes the tank. So here you can see there's an arc, and within, I would say, no time or even micromilliseconds, we were able to depressurize this small reservoir. Of course, this is not the real case because the transformers are quite big. There's a big amount of oil. So actually, the aim was just to check our simulation, in which we found that it was working perfectly. Then we took it to the lab to perform the live test. So as I said, 22 in 2022, we performed 28 tests on small transformers. EDF actually performed these. 2004, 34 test by CPIL on large transformers. You can see the setups around, on this slide. And principle was electrical arcs were ignited inside the transformer tanks equipped with a TP. So I have another video, quite interesting. You will like it. This is another test which we conducted, uh, to see how the tank is depressurized, when the arc was fed to the transformer tank. So here you can see our system is adapted here. Here is our system again on the sidewall of the transformer, and we are feeding the arc through this side with the help of electrodes, right? So when the dynamic pressure peak moves, you can see actually the shaking in the radiators, it being a hanging portion, which shows how dynamic pressure peak propagates inside the transformer and it reaches our system. So here I play, you can see here, and it depressurizing the tank. So since it's the main part, let me play it again. So shaking in the radiators and depressurizing the tank. The oil being, evacuated from the oil, or we can say that TP depressurizing the tank to ensure that there is no explosion. Now, these were the tests which we conducted in 2004 and 2008. The recent test I'll show you, which we conducted, in uh, 2002. So this is the test. Okay, this is the previous. Before that, let me show you this one. Okay, so here this is done in the EDF lab. You can find a blog about this particular test on the EDF website. Moreover, we have a detailed test report of this test, and also a witness test report by Bureau Veritas on this test. It was conducted in September 2022. So herein you can see this is the depressurization set, right? And we are feeding the arc from here, and we'll see how the system activated. Let me play it again. Just so this was actually the recent test which we have conducted in 2022, which actually showcase how fast the system gets activated. during the time when the dynamic pressure peak propagates inside the transformer to ensure there is no static pressure buildup and transformer is free from explosion. So the conclusion of these tests, which we conducted in 2002, 2004, and 2022, that TP always saves the transformer from explosion without permanent tank deformation. Now, this is the video I was talking about during one of the live tests which we conducted. We actually took this video through a high-speed camera, and we wanted to know the chronology, which actually justifies why there is a need to get activated within milliseconds, why there is no point of waiting for too long to activate the system. So herein you can see from 0 milliseconds to 6 milliseconds, the bubble volume rose up to 568 cubic centimeter, which is not small. And this is with the meters which were installed and the measuring gadgets which were there, which could actually find out that in a particular time how much was the bubble volume increase. And this 568, what we found within a time frame of 6 milliseconds. So you can imagine if we are not activating within milliseconds of when you have a fault inside a transformer, there is a high probability of getting transformer exploded or deformed and then followed by explosion. The reason being that this first phase wherein the arc is in direct contact with the oil, that's the point wherein you have enormous amount of vaporization, and that's the point wherein you have enormous amount of gases which needed to be taken care of. Otherwise, it could result in a deformation of a cover or any of the weakest part of the transformer. Now, moving further, I have a quite interesting slide wherein I have differentiated how PRV being adapted on the transformer, still the transformer explodes, and what is the reason for that. And we have made a quick differentiation between TP and PRV. Now, when we talk about transformer protector, it is activated by dynamic pressure peak. It depressurizes the tank within milliseconds and prevents static pressure increase. Tank doesn't explode. Now, when we talk about PRV, it has a spring. Now, this spring has a spring inertia of 5 milliseconds, approximately 5 milliseconds. Now, this dynamic wave, which travels at the speed of 1200 meter per second, crosses the 6 inches within a time frame of 0.1 millisecond, which is too fast for the spring to actually feel dynamic pressure peak and get evacuated or react to it, or to operate the way it should operate. So normally when the dynamic pressure peak crosses this area, it is too fast. So the spring is not actually able to react to it, and hence the PRV doesn't operate. Whereas when we talk about the static pressure, when the static pressure builds up inside the transformer, the spring gets enough time to actually feel the pressure, absorb the pressure, and react to it, and hence the PRV activates. Now, considering a scenario when PRV is open 50%. Now, again, the first factor is that PRV activates with a delay or on static pressure, and the second factor, the way it is designed. Now, when PRV is 50% open, only a small section of is there to actually evacuate oil from the transformer. And when it is completely open, 100% open, because of its design, actually, oil has to make U-turn to get deep to evacuate it from the tank, or to actually get the tank get depressurized. So this U-turn actually delay the process of evacuation. There have been a case. I'll show you one video, which is an industrial transformer. The PRV activated, but the transformer exploded. The reason being two, that the time of activation and the area of evacuation. So I'll show you that. First, let me complete this slide. So as I said, when the PRV is said to be completely open, only 80% of the 6 inches area, which is actually there to evacuate oil, is available, which is too less to have an effective depressurization. So we can say that what is the use of PRV? It is not adapted for low impedance fault. It is adapted for high impedance fault, low temperature increase, and very slow gas creation. Now, let me take you to this video, which is quite interesting, and I'm sure you will like it. This video is actually coming, from just a moment. Uh, Okay, I'll take you. I think I'm not able to get that stuff. I'll show you this. There is one video. Let me. I'm not getting the access to it. Okay. So okay. So I have this video. This is actually an industrial transformer, small transformer, and you will see that the PRV activated. Now here is the transformer. The PRV activated, but the transformer exploded. There is no sound, just for your information. So you have seen here that the PRV activated. There was a flow of oil from the transformer, but the transformer exploded. The reason being the PRV is getting activated on a static pressure. That's why there is already a delay, to have activation to depressurize the tank. Secondly, the amount of oil which should have been, evacuated from the transformer was not enough. It's like a pressure vessel. You have given it an opening, but the opening is not enough to depressurize the tank completely. And as a result of it, the transformer exploded. So two factors: time of activation, and secondly, the evacuation section. I would say it in rather different words: the size of evacuation, which decides the amount of oil which moves out of a transformer to actually depressurize the tank. Now, going back to our slides. So now, as we talk about okay, this is just to show you how the rupture disk activates. This is a good video. So this is one of the video again we took during the live test. This is how you can see the grooves. You see the grooves inside the rupture disk. So the rupture disk actually opens up from here when there is a fault inside the transformer. So now moving to our configuration, wherein how our system is designed, what are the components. So to quickly cover it, and then we can come on the question and answers section. The components are vertical depressurization set, which is mainly for the main tank; oil bushing cable box protection, which is for the oil bushing cable box; OLTC depressurization set for the OLTC. Slice OGST is for, as I said, to make the structure compact. We just request transformer manufacturer to extend the consumer tank and give a partition, which serve as slice OGST. TP cabinet, TP control box, explosive gases evacuation pipe, inert gas injection, and linear heat detector. So few of our designs, although we have several designs, that purely depends how your transformer is designed, which allow us to design our system. We are a customizedly designed system, right? And for each and every transformer, of course, if the same transformer is there, we'll have a same design. Now, detailed component, quickly covering it: vertical depressurization set to relieve overpressure and initiate high-speed depressurization. Size varies and depends on the transformer, and it includes isolation valve, shock absorber. Easy to maintain. You have isolation valve. You just open and close it to do maintenance on the transformer and maintenance on our system. And these are the different configuration we have. It can be adapted on the sidewall. It's a 45-degree, which can be adapted based on the requirement of the transformer tank. Then we have oil bushing cable box DS, which looks like this. Then we have OLTC depressurization set, which looks like this. I'll show you the real installation pictures as well. Slice OGST, just for your reference, this is how the slice OGST is done. We have this model installations already in India. Then we have other retrofitting cases installation. You can see here it's wall mounted OGST, and this is elevated OGST. Inert gas injection set, you have different elements which helps to have the nitrogen injection inside the tank, and we can actually measure it. Control box, which can be PLC based, it ensures logic of the TP, and it is UL listed. Retrofitting, yes, TP can be easily adapted with the new as well as existing transformers. So we look for a manhole on a transformer which actually meets our sizing requirement. As I said, for 100 MVA, we look for 8 inches. And if it is not 8 inches, we never use the adapters, right? And we never use a manhole which is lower than the requirement of a size. If it is there, we never take that project, or we never install TP on it, because that will not give a effective depressurization to the transformer tank. And this is for the nitrogen injection, how we do it. Now, TP comes with several options. As I said, it can be customizably designed. There are a lot of options which can be discussed with the client, which allow you to make it, uh, to have more, let's say, options inside to make it, let's say, having additional functions inside the transformer protector. Additional point is that the TP comes with a liability insurance coverage of 15 million euros. Should a transformer explode with TP installed in it on, in service position, Zurich is liable to cover losses up to 15 million euros, which is equivalent to about 130 to 150 crores. And this insurance actually runs for the whole life. Every year it is renewed by Sergi without any cost to the client. So every year, the end user receives a certificate being a co-holder of a policy along with Sergi. So something happens to the transformer or the transformer explodes, end client can directly write to Zurich claiming the amount. That's a complementary feature of our system. Now, taking you through quickly through, as we have limited time, I'm just taking you through quickly through few installations so that you can analyze how the TP installation looks like. So herein we are using 45-degree DS, mounted on in a hydropower plant. This is how we have designed it. Then we have again elevated OGST. This is vertical depressurization set. You can see here it's OLTC depressurization set. Here we have elevated OGST, vertical DS. This is 45-degree cabinet. You can see here wall mounted OGST, the horizontal depressurization set. This is vertical depressurization set. This is oil bushing cable box protection. So you can have an idea how the TP is installed on the transformers. This is NAM power. NAM power, the TP got successfully activated here. And, it has got one vertical DS. It's 315 MVA transformer and 3 OLTC installed. And we were able to save the transformer. This is in France, Nenden hydropower plant. So we are protecting the transformer inside a cave. In Qatar, you can see it's main tank protection on the side wall of the transformer, OLTC protection. Then we have cable box protections, nitrogen injection, TP cabinet. This is for Australia. This is our certificate for the life test, which we did in 2004. Then we have certificates for the other test also, which we have done. Okay, on my side, this is a brief about our system, right? And, a detailed explanation about the principle and other, description of physical description of our TP as well. So now I invite all the question and answers, hoping we have enough time to talk about that.
Thank you,
Uh,
Rahul Sood. Thank you very much for insightful presentation from your side. Before I invite some question, I have small queries on behalf of all
yes.
the participants here. Very basic question from my side. What is the success story of the FDS in India?
Okay, the success story, we have successful activations with Tatas in India, already have, although we came late, we started doing business around 2016 or 2017. We already have a successful installation, successful activation in India with Tatas. We have our installation in generation with one of the renowned utility in India. We have our installation in transmission, again with one of the utilities in India. We have our installation in private sector, ArcelorMittal, they are using our system, right? And yes, we have recently seen much interest from other utilities as well. In fact, we have replaced conventional technologies with TP. So that's what I can proudly say that we have been able to deliver up to the mark of the utilities, and we are continuously receiving interest, to give presentations or to to give them some idea on replacing the conventional technologies which is already there on the transformers.
Rahulji, another very common question from my side. Suppose you are going for the retrofitting of that system for existing transformer of any make. Do you get permission from OEM before going for that system, or you can do that thing?
Well, normally, since we are not impacting the efficiency of a system, efficiency of a transformer, because we are externally adapted, Normally, OEM do not have any issue adapting TP on the transformers. Just I take this opportunity to let you know that we have worked with almost all transformer manufacturers, even based in India, the Indian manufacturers, even from worldwide. We have reference with almost all transformer manufacturer, and we have never faced such issue anywhere, even in India or outside India.
And Rahulji, as per India is concerned, it is governed by CA rules, some IC rules, and CA standard for transformers, CA safety standard. I couldn't find recommendation of this FDS in any of the document in India. What do you
Okay.
think about it?
Sure. See, CEA never, I would say there is a regulation in India which says that there should be a nitrogen injection system installed on the transformers. But of course, CEA did not define the technology to be adapted, right? It keeps it in the hands of utilities or the owners of the transformers to decide which technology they would like to go for. Now, I would like to invite you to visit CEA, wherein there are series of reports of failure investigations which CEA has done in the past. Now, I refer to one of the reports wherein there was an explosion on the transformer, and there was a transformer failure and 315 MVA transformer, and it was having conventional transformer protection, which is very much common in India. And the transformers still burned and exploded, and there was a big defamation on the transformers. So while investigating that case, wherein they clearly mentioned that the conventional protection couldn't save the transformer, even though it operated, it couldn't save the transformers, and it is very slow. Fast depressurization systems must be explored and must be looked into for the future orders. That is one. Now I invite you to another document, which is minutes of meeting. In fact, wherein all all manufacturers who are manufacturing nitrogen-based system were invited, and they presented their technology, and CEA as their analysis or their view was where they clearly mentioned that system should be self-sufficient and should not be dependent on any of the external signals to activate. Now, these are the findings coming from the official documents which are there on CEA website. You can access it and you can have a look, or I can pass those documents to you.
Okay, now before I invite question, last question from my side. In all nitrogen injection systems of any make, parallel to that, there is some connection going to my relays so that I can isolate my system.
Mhm.
But in your presentation, I couldn't see any control system that is giving command to any relay inside the control loom so that my system can be isolated during the problem in the transformer.
Okay, it's a very good question. Here, I would like to, and in fact, I thank you for this question. Now, our system, as I said, it's not dependent on any of the signals to activate. So, what I am doing, what I'm saying is that we activate mechanically. So, the rupture disk actually works on the increase in the pressure. So, when there is an increase in the pressure and it reaches to the calibration level of rupture disk, the rupture disk bursts. Now, the signal from, we provide double burst indicators over this rupture disk. The signal from this rupture disk can be taken to trip your transformer, to the circuit breakers to trip your transformer.
Do you have provision for that?
Yes, exactly. So we give that, and moment our system activates, the transformer is isolated, and then it moves further.
Sir, but you claim that it can operate in 5 seconds, 5 milliseconds to 20 milliseconds, but you haven't added the tripping time of my relay and tripping time of the breaker associated with that relay.
Sir, we claim that our system gets activated. When I say that my system is getting activated, is a burst of a rupture disk.
Okay.
This burst of a rupture disk happens within 0.5 to 20 milliseconds, which gives subsequent signal to your circuit breakers to open up. Right. So my system, even it has been proved. I mean, one is our live test, which we have conducted. Secondly, we have seen the SCADA logs of the clients wherein we got successfully activated. They have actually shared the SCADA logs wherein we can say, and we can see actually that our system is getting activated within 5 milliseconds. And these documents are testified documents by the end user itself.
And finally, what happens when you are going to purchase any system? All system must be type tested.
Right.
What do you say about that?
See, as of now, if I have to talk specifically about Indian market, of course, I'll put some, share some information about the market in South Asia too. Now, in India, what we have as such, we do not have any standard for the same, right? So normally, how it started that there should be a functional test of the system, right? Which was a story started by conventional players in the field of protection. Right now, functional test system does not give you the exact scenario wherein I believe functional tested is something that that's my view how I see functional test as that you press a button saying that okay, consider it as a PRV signal coming in. Then let's say if you're working in a logic, then you press another button and saying that okay, let's consider this is Buckle's relay signal coming in. Then you play with that logic to say that my system trips in and my system activated, and this is how we activate. I do not believe when you're working with such a critical asset and a high value asset and you are not getting your system actually type tested, I would rather say live tested, which was the word used by one of the renowned utility, which actually issued a notice saying that if your system is not live tested, either you make your system live tested, but we will not accept functional tested, because they were already facing several issues with the conventional systems. Right. So as if I have to talk about TP, we have done, as I said, around 80 live tests. Live test is we create different scenarios. We consider different megajoule of energy. The latest test we conducted was creating a megajoule, 40 megajoule arc in line with how IEEE explained 40 megajoule arc, and we tested our system. And we found the TP successfully saved the transformer, and it has been justified or witnessed by Bureau Veritas. So since there is no standard, what we can rely is mainly the live test, how a system perform in a live condition.
Okay. And I will be failing in my duty if I don't invite respected honorable legends available P. Ramachandra Sarji, and
Sure.
kindly unmute sir and give your view on the technology he has already explained.
Mr. Aroraji, I don't have much to say on that. So far my experience is that this type of all systems it takes a lot of time to operate, and many times it may not operate also. It's true that live test and all is okay, but when you are any system, if you are asking it to operate after 10 or 20 years of idling, then whether this will work or not, I have no idea. And also, if this is so popular, but if you check many European countries also, they are not adopting this sort of thing. They are still going with the old water spray system, emulsifier system.
Okay.
So this is my knowledge so far. And even this high pressure system, they themselves in their catalog say this system will not be effective if the fire is from a bushing.
Okay.
Because bushing is outside. So all this rupture and all will happen if the arcing is inside the tank. Suppose the bushing fails at the top and the bushing porcelain shatters and it catches fire. So the pressure by the whole this system will not work at that. Of course, they themselves in their catalog they have said that is the limitation of the system. So we should be very clear about. And you yourself, as in your introduction said, most of the fires in India are from bushing failure.
Yes, 22% I have seen in the document.
Yeah, yeah. So this is the limitation of the system. So I always suggest to utilities, instead of going for a system that you think that it will protect your transformer or extinguisher, there are so many passive systems that you should follow, just like a firewall or the things that will not spread the fire. So this is, and see that this type of failure is not happening. And one more point, at least for the interest of those who are attending this seminar, we all should remember that basically transformer oil has the arc quenching property. That is why in the textbook we have learned now. Earlier times it was all oil circuit breakers where transformer oil was used to quench the arc.
Right.
So this is the proper. So in transformer also, suppose there is an interturn fault or a fault at the neutral end of the winding or in a tap changer, that is not auto transformer, different. No? Only I am talking where neutral tap changer is at the neutral end of the transformer. You will see that fire is never or almost rare. No, it will not happen. Why? Because when the fault is at the neutral end of the transformer, the energy or the arc current is reduced. And the arc energy depends on three factors. One is the current, arc current. Two, the time for which the current is flowing. Three is the arc voltage. Arc voltage is not the same as the line voltage, 400, 760. No, of course, with the 400 and 760, the arc voltage also will increase. So this is the total thing. When this goes up, then the arc goes inside the transformer. So this type of very high arc energy is from the low impedance fault. That is the fault at the line end of the transformer. Suppose bushing tail fail. This is a direct, what will happen? Direct 220 kV or 400 kV grid will collapse inside your tank because there is nothing to stop. But if the fault is at the neutral end of the winding impedance will stop it. And the maximum current can only be whatever the rated current divided by the percentage impedance. That is the only current it can come. But if the line end, it may be 20 kA, 30 kA, like that it will go. Then what will happen is the huge energy goes to the ground. Then that arc temperature is 2000 to 3000 degrees centigrade.
Ooh.
This will immediately vaporize the oil. And remember, 1 cc of oil, when it becomes gas, it may be 100 cc or more. No, that is the times expansion is so huge, the gas volume generated. Because of the huge gas volume generated, the pressure develops because the tank has only this much volume. If it is 100 times gas is coming, then that is the way this wave, so the pressure, dynamic pressure wave starts. So even this system also, the ruptured disk, suppose the fault is very far away from this ruptured disk, then there is limitation. By the time it reaches the ruptured disk, the tank will rupture.
Oh.
And how it catch fire, that also be very clear about how it will catch. As I said, if it is a neutral end, it will not catch fire. But if it is a line end and very high pressure, this huge volume of gas as a pressure wave, maybe 15 bar or 20 bar, it moves and shatters the tank edge, the welding or whatever, and the gas will not have cooled by that time. As I said, the core temperature of the arc is 2000 or 3000. When it comes to the tank and this hot gas comes out, this is all petrol, just like petroleum gas, no? These all hydrocarbon gases, combustible gases. When this comes out to the air, the oxygen comes in and it starts fire. The fire starts. So the fire is not starting inside the tank. Please understand. It will always come when it comes to the outside. That is why sometimes you will see suppose the bushing tail fails. If you are lucky and your system is not very strong, then what will happen is inside and all the problem will be there. Still fire will not be there because the oil will extinguish or quench the arc. I have seen this sort of thing in a 400 kV 315 MVA transformer. Bushing, one of the bushing bottom tail failed because excessive pull came on the top terminal of the bushing because they have connected a very a small length jumper connection that was done in summer. And when the winter came naturally, that because the temperature difference, it contracts. And then tremendous pull came on the bushing, and early morning in the coldest day of the winter, the inside the porcelain broke of the bushing, and the whole inside the tank was completely carbon, and there was arc, and it all happened. But fortunately, the tank did not rupture. Of course, small rupturing, but by the time the gas failed, there was no fire. So even if there is no fire protection system, most of the cases these days, it may not start a fire. But then normally what people will say who has put up the system, oh, see, look, because of my system, it failed. Now, even if there is no system, it will not happen. No? So all the arcing may not cause a fire, but certain type of this line and fault can cause a fire. That is why, like a 315 MVA transformer or 760 transformers, now PGCL is thinking of removing the tap changer. But there what happened is, a tap changer is a 220 kV potential. Suppose, and you have seen that diverter switch where you put the oil. Suppose that oil become deteriorate and you are not doing anything. Main tank you may be processing. If that is oil is deteriorated, what will happen is that the terminals are 220 kV, the oil TC contacts. So that from there will be a flash to the ground, upper tank, because only that FRP pipe, the cylinder alone is there. So this rupture, this arc will go to the upper tank. There also the 220 kV line is connected to the tap changer. So the 220 kV grid will collapse into the tap changer and fire starts. So there are 3 or 4 reasons for bushing fire transformer. One, as we said, the 220 kV or the HV bushing, because the entire grid will collapse and then starts fire, or line and tap changer. 3 is the cable box, oil to oil cable box. These are the 3 main reasons for the transformer fire. And many times you will even see this LinkedIn and social media engineers are writing because overload will never cause a fire. Also not due to high winding temperature. No, nothing will happen. It will happen only if high energy arc is there inside the tank. That is a low impedance fault. So as power engineers, we should find out what are the reason for the bushing of the transformer fire and take countermeasures. And don't go for protection system to take care. These are the main points you should take. Of course, there may be very critical transformers. There you can have this whatever high depressurization system and all these systems we can implement. But unfortunately, in our country, as a mandatory, we are even 5 MVA transformer, we are going to putting. And I have a logic always, I used to say, these are not very cheap. All are very costly. No? And we all know that how many transformers, the fire, the percentage failure in India, we know how much. If there are 1,000 transformers, there may be fire only in one. No? And instead of this one, we are putting all the money around 1,000. So wherever collateral damage we cannot allow, or there are systems, then we can have very costly systems we can have. But a universal adoption of any of these systems, I do not feel that it will be effective. Anyway, this is my personal opinion.
Thank you. Thank you, sir. Thank you very much for your opinion once again. Now I would like to invite 3-4 questions. Kindly raise your hand and I will unmute you. And you will be able to talk directly to Rahul Sood. Kindly raise your hand so that I can understand who wants to ask question. Please press raise hand button bottom of your screen. Murthy Saab, yes, welcome. Gulab, unmute Murthy Saab first. Welcome, sir. Welcome, sir. You are muted.
You are able to see hear me.
Yes, yes, please continue.
So as Mr. Rahul Sood has said that no protection is needed, particularly supposing as Ramchandran Sahab has already explained elaborately. So I have nothing much to say, but yes, he has not told about any this what you call um, a valve which will get closed after the oil is being drained, okay, from the conservator. That he has not told, okay. And number two, as you have already said, that there should be some indication going to the control room. That is also one of my questions
Rahul,
that we have already
can you explain
asked him.
the operation of valve during that rupturing of your this?
Yeah. Okay. Hello, Moti ji. Good evening. I thank you for the questions which you have posted. I take one of the concern from Ramachandran Sarji as well. He mentioned that if the system remains idle for long, there is no surety on the efficiency of a system. So I would here mention with our successful activations, wherein we installed system in 2002 and we saved the transformer in 2012. So this.
See, all said and done, the PRV is there not in one place, but on the transformer top, it is at least in two places. Okay. So that PRV is bound to operate when the pressure is developed. So it will not wait for your system to operate, you see. And if you say that your system is so foolproof, then why do we have PRV and why do we have the other protections? Okay. So it is somehow I cannot understand. See,
Okay.
so if you're
Yeah.
having your system, okay, and you please let me know how many this utilities in India have purchased your system.
Okay, sir, I'll answer your question line by line. Talking about having the PRV, whether the transformer has got 2 PRV or 3 PRV, we are not questioning the number of PRV, and we never advocated that the protection should be removed. We mentioned that PRV works on static pressure, and which is too late for the
PRV starts operating 0.47 milliseconds. Okay, 0.47 milliseconds. The PRV starts operating.
But sir, it will operate, sir. It will only operate when it has sensed the pressure, and it's.
No, but then, as Ramchandran Sahab has said, that pressure will not develop that much if the fault is near the neutral. Okay, so for any fault in neutral, even differential relay does not matter, does not operate. It is the restricted earth fault relay that operates.
Sir,
Okay.
That's what I said.
So,
We never
supposing
Please go ahead.
No, somehow you tell me how many utilities this the biggest utility, central utility in India is Power Grid. How many such utility?
Sir, that's what I'm answering you line by line. As I mentioned earlier, also we are not advocating removing either earth fault protection, differential, or PRB. We never said that need to be removed. They are there for the purpose, right? As you said, for the neutral, if there is fault in neutral,
I
okay.
agree that I agree to your thoughts, but the largest utility in India is Power Grid. How many equipment you have supplied to Power Grid? You tell me.
We have only supplied one until now, but which is yet to be installed. And I'm
No, where to Power Grid or to some
yes,
Tata?
to the Power Grid, sir. You asked me about Power Grid. I'm telling you about Power Grid only.
So what was the MVA
It's for a 85 MVA reactor in Bhiwandi.
Pardon?
85 MVA reactor. Yeah.
85 MVR means it must be reactor, isn't it?
Yes, exactly.
So
no, sir. My point is what I'm saying that
I would like to have your technical detail. If you can forward it to me.
Sure, sir.
You can have
I will
my
share,
email.
I will share. Don't worry.
Yeah.
Any question from other participant? Kindly raise your hand in the meantime.
So hello, may I still continue? Any of the this OEMs have provision for your equipment in
Yes,
India?
sir. If end clients want our system to be brought, OEM give the provision. Just for your information, we have supplied with BHEL, we have supplied with CG, we have supplied with Bharat Bijli, we have supplied with TBA, we have supplied with almost all Indian transformer manufacturers, not only in India but abroad also.
Okay. So thank you so much for giving me an opportunity.
Any question from any other participant? We are open. We are waiting for the question. Umesh Gupta ji wanted to ask some. Yes. Neeraj Kumar Singh. Welcome, sir.
Sir, good evening, sir. My question is, what is the probability of mal-operation during the case of a closure fault outside of the transformer?
Okay, you mean if the fault is coming externally, right?
Yes, yes.
Okay. See, for any external faults, which TP activation is mainly, let's say, if that external fault gets inside the transformer, right? In that case, the TP will have its functioning to depressurize the tank, right? When I say external faults, probably we relate it normally with the having it through the bushing, right? For bushing, as Ramachandran said, sir mentioned that when you have porcelain part getting broken up and the fire getting there, in that case, Ramachandran sir is completely right. We work as an on our extinguishing mode, wherein the nitrogen will be injected. However, as an additional protection, we protect bushing turrets, wherein we put a rupture disc. So in case there is an internal fault in the bushing turrets, that will be taken care by our system.
Umesh Gupta ji, kindly unmute and go with your question.
First of all, I would like to thank Dr. Rajesh and Mr. Rahul. I think he has given a wonderful presentation from his side. As far as technology is concerned, new technologies are coming for critical applications, and Ramchandran Saab and Murthy Saab, they have also given their views. Many times, such systems, when installed on transformers for critical requirements, may also attract different kind of views, as we have already listened. So it's evolution of the solutions, I should say, and to learn for all the engineers during this course of evolution. So my basic question to Mr. Sood is, we have already have NIFES in system, and you are now coming with TP. So though some of the difference we are clearly having with us, but I would like to know from Mr. Rahul that what is the basic difference between the two systems, NIFPS and your transformer protector.
Thank you, Umesh ji, for raising this question. Well, the difference between the existing technology, which is their NIFPS and transformer protector, is on the two parts. First, the operation, the principle of operation, because NIFPS is dependent on the signals from your transformer protection. If there'll be signals coming from your transformer electrical protection, only then the NIFPS will work. There have been cases where we have seen, even though there were signals, the system didn't work. That is the first basic principle which relates to principle. Second one is the protection level. Now, the protection level, TP brings in protection for the main tank, OLTC, oil cable boxes, and bushing turrets, whereas NIFPS is limited to the main tank. That is second one. The third one is the customization. As I said, the TP comes with a customized solution for the transformer ranging from 0.1 MV to 1000 MVA. And to justify that, we have several sizing requirements suiting the need of the transformer of different rating. Whereas when we talk about NIFPS, there is always a draining for 4 inches valve, right? And moreover, when the system activates, it needs to displace the oil up till the butterfly valve, which opens inside, blocking the flow from 4 inches to 2 inches or 5 inches to 2 inches, which takes time. First, NIFPS has got time taking from the signal being received from the electrical protection. then the butterfly valve getting opened up from inside and then displacing the oil from the brim of a transformer up till the butterfly valve. That takes additional time. Whereas when we talk about transformer protector, it activates within milliseconds because it is not dependent on any of the electrical protections. And secondly, the moment it activates, the tank gets depressurized. That's the basic difference which comes on. And I would like to add here that TP during a case of, let's say, if there is a scenario of a cyber attack, which is of course, it's getting more and more popular. I would say not that much in India, but the cases have been seen. If, let's say, a grid is being cyber attacked, TP is the one which cannot be hacked. And even if the differential protections are changed, TP will still save your transformer, which is not the case with NIFPUS, because NIFPUS is taking signal from your electrical protections. Moreover, once you have your electrical cables getting burned off, the NIFPUS will not work, TP will still work. We have our efficiency, a case wherein we activated even after getting installed for more than 10 years.
Thank you, sir. And the last question from Sundar, sir. Sir, welcome. Kindly unmute and start your question. Last question of this session.
Hello.
Yes, sir. Welcome.
Namaskar. Actually, system seems to be good one. Just like you use in the LT, low pressure turbine, the rupture disc. This is like that only, but there is a lot of limitation as Ramachandran sir told. We just think of that PRV, what we use, the spring loaded. We can have this one in place of PRV, one of the PRV. We can have this one. What experts can tell?
Sir, I mean, we do not recommend replacing PRV. Along with the PRV, which is a standard design coming from the transformer manufacturer, it is additionally adapted on the transformers, externally additionally adapted.
Yes.
So we never recommend replacing PRV with TP.
It is important to mention here for all the participants that that is not something to be replaced with this technology. That is additional safety requirement that is to be installed in your transformer along with the existing protection devices you have already installed, like PRV or whatever you have already installed.
Yes. Yeah.
And,
okay, that then it depends cost point of view. You have to evaluate how much benefit you will get.
Yes.
Of course, sir. Cost point is very important when we see that we are one of the I mean, cost really matters since we are such a big country and we have more than we have huge number of transformers. But of course, if we are comparing with the conventional technology which is there in India, we are on a higher side for the reason that you have limited protections within with the conventional one, and with our system we are coming up. We have the complete safety of your transformers. So, and moreover, the cost is directly proportional to the protection level we provide for a transformer. So rather than giving you any vague figure, I would suggest if you could share some information. Let's say I'll give my email ID to Rajesh Arora ji. You can send us that information.
All are in the IP group. They can approach you.
Okay.
They can approach you easily.
Sure, because we need to have some details to actually work out on the pricing side of TP for a particular rating of a transformer.
And with that, we are running short of time, and I would like to say thank you to all the participants who spared their invaluable times and joined us. And thank you to Rahul Sood ji for discussing about the new FDS technology. With that, thank you everyone. Thank you.
Thank you everyone for your presence. It's really nice to be here and present our technology. Thank you very much.
Thank you very much.